Okay. So what we've done so far is to look at the energy band diagrams, right? And one of the things we've seen is that if you have essentially a semiconductor or any material, you have these energy bands, any solid state material, you have these energy bands. And when you have a situation where one of the bands at 0 Kelvin, let's say the valence band, is completely full and a conduction band that's completely empty, you can, as you raise the temperature, you will have electrons and holes generated. So what you will have is that an electron jumps from the lower band to the higher band, so you will have an electron, and what it leaves behind is a positively charged area, which we'll treat like a particle and we'll call it a hole. Now, with this in mind, what's going to happen is that if this is a pure material, what can you say about the number of holes and the number of electrons at any point in time, at any given temperature? They would have to be equal, right? Because they're both generated through this thermal generation process, and what happens is that they will have to be equal. So yes, as you raise the temperature, the conductivity increases, it becomes less resistive, but that's almost all that control you have. Now, if you want to make something, useful, you ideally want to be able to control these electrons and holes independently, right? And that ability to control these electrons and holes independently is very important because it allows you to design devices, make things that do some useful things. So the question is, how do we come up with a scenario that we can actually control these number of electrons and holes? So one of the things to keep in mind is that the situation we described for carbon earlier is also replicated. So this is basically column 4 of the periodic table. This is column 5 and 3. So you have carbon, you have silicon, you have germanium, and then you have tin, right? In this, SN, tin, in this level, in this column. Now, all of these form a similar lattice structure as diamond. So this would have a diamond lattice structure. Now, but still, that lattice structure, which we will basically show a two-dimensional surrogate for like this, will have electrons and holes generated, but beyond that, because you have four n states that are full and 4 n states that are empty, if you have electron hole generations, they would be symmetrical, and there would not be much to do with that. So now the question is, how can we do something about this? What can we do to change the ratio of electrons and holes? Because that would be a useful thing to do. You want to create a situation where you can basically have more holes than electrons, or vice versa. So, yes? Right. So you can introduce elements from column 3 or column 5, and this process is called doping. So the elements in column 5, so we have nitrogen here, you have phosphorus, arsenic, and I think that's the next one is antimony here. So what if you introduce a column 5 element here? Well, let me just change the color of this thing to make it look different. So you have nitrogen, phosphorus, arsenic, and antimony. So what if I take one of these atoms and replace it with a column 5 element? So what would happen? So you have still the 4 electrons that would try to form 4 covalent bonds, right? But there would be a 5th electron associated with this one that doesn't have anyone to bond with. Right? So there are 4 bonds formed already, and this is here. So it appears that this electron would be much more loosely bound compared to the other electrons. Now, we can actually see this quantitatively, because if you think about it, if you take away this electron, this will have a positive charge, right? This area will have a net positive charge. This would be an ion. This would be a positive ion, because the nucleus, the only difference between, let's say, phosphorus and silicon, or arsenic and silicon, is that phosphorus and silicon would be that phosphorus has 1 extra proton and probably possibly a couple of extra neutrons, which are not important in this discussion, in its nucleus, right? So what happens is that now you have this positively charged thing sitting in the middle, and then you have the electron. So the question is, this electron that you're talking about, how tightly or loosely is it bound? How can we calculate it? Well, the good news is that we've already done the necessary calculation, almost all of it, right? Which is here. So the energy levels or if you look at the energy level that we calculated for the hydrogen, was given by this divided by n squared. So now, what is different between a hydrogen in free space or whatever, silicon in free space, and when you are inside a material, inside a crystal? So what happens, what's going to be different here? Epsilon, right? Yeah. So the permittivity will change. Now we'll talk about why, we can talk a little bit about it. But so let's say the permittivity changes. So the relative permittivity of silicon, so epsilon relative of silicon, is 11.7. So what happens is that in this calculation that we did before, epsilon, now epsilon, this is going to get scaled. So this energy level, let's say the hydrogen. So this kind of looks like a hydrogen if you think about it, because it's a positive, one positive charge, one electronic charge positive and one electronic negative charge, except for the fact that it's inside silicon. So now you're going to, this is going to get scaled by epsilon r squared. So your 13.6 eV is going to get scaled by that. So the largest energy level that you will have, it would be 13.6 divided by 11.7 to the squared, which is roughly 0.1 electron volt. So the bonding energy of this electron is only about 0.1 electron volt, about more than 100 times smaller than that of, for example, of a hydrogen. So this is a much more loosely coupled electron. So it can be much more easily, with slight amount of thermal energy, it can be released. So this electron is much easier to release than these electrons. So these electrons can go around very quickly, right? They're not tightly bound. Now you may come back and say, well, wait a second, what do you mean by epsilon? Is epsilon relative and epsilon? Because epsilon is the quality of bulk material, and you're talking about atomic levels and things of that sort. And what's really happening? Well, that's still valid. What gives rise to, if you think about it, the dielectric constants? What creates dielectric constant? What is it that's causing that? What would cause materials to have dielectric properties? To have epsilon relatives greater than 1? What is it?
The existing electron cloud kind of screening the electric field.
Sure, exactly. Atoms get polarized, right? So you have electron cloud that moves slightly with respect to the center of the positive mass, so you will create an electric dipole, positive, negative. And that still can happen, because you have all these atoms around and all this electronic gas. So everything around it can still be subject to that. So this movement of electron in that space, in that area, despite the fact, because of the fact that you have all these electronic gases that can displace with respect to the center of gravity, center of charge of the positive and negative, and that displacement can create electric dipoles. So this is still a valid thing to do. And as a result, you will see that this energy level is much smaller. So the way it looks like in the energy band diagram is different though. So now you have these energy levels associated with these dopants. These are called, by the way, donors. The column 5 elements would be called donors, because obviously they donate electrons. And what happens is that now you have these energy levels that are here, very close. This is like 0.1 eV. An electron can jump from here and form a free electron. And what would be left behind? A positive ion, right? Now, this electron obviously can move around. This is a free electron. But is this also a hole? Why is it not a hole? What is different between this and a hole? Yes. Yes, why can't it move? Because this positive charge is contributed because of what? Because of its nucleus, right? So this is fundamentally different, as you pointed out. It can't move. This guy is bound here. So yes, there would be a positively charged area here, but it's not a charge carrier. It cannot carry any charge. All it does, it just sits there. And that's why this energy level is shown with broken line, not with a straight line, because there's no transition across that allowed. So whatever happens, whatever is released, there's an ion, they're fine. There's an ion. Now, so that's for that. Now, this way, we can create materials that have actually more electrons than holes. So we can artificially control the number of electrons and holes this way. Now, what if we wanted to do the opposite? What if we wanted to create a material that has more holes than electrons? What do you think we should be doing? Any suggestions? I want to do the opposite. I want to create a situation where I have more holes than electrons. Go to column 3, right? So on column 3, what are the elements that we have in column 3? So have boron here, and then we have the aluminum. This is gallium, and this is indium. That's right. Thank you. Indium. So what happens is that you have the column 3 elements. In particular, so by the way, when we talk about donors, the donors that are typically used in semiconductor almost always are these guys. And for acceptors, so these are donors and these are acceptors, the ones that accept electrons, as we'll see. We usually almost always use boron, for silicon at least. So let's say now what we do, we introduce a atom with from column 3 here. So what's going to happen? It's going to be 1 electron short. So if it's 1 electron short, there's one of these bonds that cannot be formed. Now what happens is that, but now this is a bond that can be opened and closed pretty quickly, opened and broken and formed rather rapidly. So what you can do, one of the adjacent bonds can break, and you will have a positively charged area. And this guy becomes negatively charged. So this is going to be negative E. Now it's a negative ion. But again, the same way, this ion cannot move. But this hole that you formed here now can move. So this is an acceptor level, energy level. And the way you show it, again, is an energy level. So this is E acceptor, and that was E donor. Which basically what it means is that an electron can be released from here, go in there and get stuck, but then you will have a hole left behind that can move around. So this way, by introducing acceptors to the lattice, column 3 elements, you can actually create a situation where you have more holes than electrons. So you can control the number of holes and electrons independently. And this is very important. So a couple other comments on this. So now, but what determines when this gets ionized? When this ionization happens? Well, it's the temperature, right? If you think about the number, let's say you have a donor situation, you have a donor introduced, and you're looking at the number of electrons shown with N versus the absolute temperature. So what is the number of free electrons at 0 Kelvin? In a situation that you have the donors, let's say you don't have the acceptors, so just like have the what would be the number of electrons when at 0 Kelvin? 0, right? Because there's no energy for anything to get ionized. There's not even 0.1 EV, so nothing's going to happen. So as you start raising temperature, what happens? So let's say, just before we do that, before we do that, let's talk about a special scenario. Let's say you talk about a pure semiconductor for a second. If you have a pure semiconductor, as I raise the temperature, what will happen to N? It would go up, right? And it would go up exponentially. We'll see why in a few minutes. But that's what. Now, let's say this time you have the donor levels. Now you have the donors in there. What would happen in terms of as you raise the temperature?
Start going up much more.
It starts going much more rapidly. Why? Because these guys require a lot less energy. It takes a lot less energy to take an electron from here and put it there as opposed to from here to there. Right? So initially, it goes up exponentially, but much more rapidly. But then at some point, you will have ionized all of them. So what happens? It flattens. And this would be basically ND. The number of electrons would be equal to the number of dopants that you have introduced, because they're all ionized, and that's it. And then how long will this last? So once you get close to this thing, then now the thermally generated electron hole pairs would come in, and they would basically be dominating it. So if I ask you, what is a good place to operate a so let's define 3 regions. Region 1, region 2, and region 3. 1, 2, 2, and 3. So if you want to use it in a useful structure where you can control the number of electrons accurately and all those things, which region would you use it in? Region 2, right? Obviously. So that's the good region to use it. Now, how about use region 1? Let's say you want to make a device, make a semiconductor device that's used for cryogenic applications. Let's say you're trying to make it very low noise something, and you're just trying to make a cryogenic system. What should you do? Does it mean that you can't use it? If you knew that you're designing a device for a cryogenic temperature only, and let's say you wanted to have this level of charges, what would you do? What's one of the things that you could do? Let's say you wanted to operate at this temperature. Lower ND or higher ND? Now, let's say I want to be at this level, right? So if I start off with ND that would get me up to that much higher level, but it is at that level at that temperature, I can still make it work. They would not be all ionized, but the number that will be ionized will give me the sufficient level that I need. But then it won't work at higher temperature. I just overcompensate for it, right? Yes?
Is there a good alternative to that if you're worried about temperature stability?
Yeah, that's a great question. Because, so that device would not be very temperature, because slight changes in temperature would change the number of carriers. So it can get temperature thermal variation. The alternative to that is basically just use what you have, right? And also, there are certain types of semiconductor that basically create energy levels that are smaller. But if you're operating at very low temperature, let's say liquid hydrogen or liquid nitrogen or something, I mean, liquid nitrogen is not that low, but liquid helium, not liquid hydrogen, liquid helium, if you operate at liquid helium, then essentially you either have to overcompensate or live with what you have.
What did you say region 2 is optimal for?
Because the number of electrons, the number of free carriers is well controlled and is stable, right? So you can control it by doping, and it will remain stable in that region, the number of free electrons that you have. And how about region 3? Is region 3 useful? I mean, as a well-controlled device, probably not, because this is just like, now it's becoming like what we call an intrinsic semiconductor. The doping is not doing anything, essentially. For all intents and purposes, doping is not there. So we want to operate in region 2, generally. If we can, region 1, there's ways of using it. You have to be careful. But generally speaking, you want to be in region 2. Now, there's another thing. We talked about semiconductors. So silicon is one of the typical ones. Before, in the past, germanium by itself was used. When I was a kid, the transistors I used were half of them were germanium transistors. And germanium has a smaller band gap than silicon. So let me ask you this question. What's the problem with a germanium transistor if it has a smaller band gap than silicon? What would be the problem with that? Yeah, less temperature stable. That's correct. So what happens is that this thing happens earlier at a lower temperature, right? This orange curve will come in. So as soon as it heats up, it starts getting pretty bad, right? So you have to be careful about that. Now, there's also other kinds of semiconductor you can form. You can form compound semiconductor. For example, you can take an element from column 3 and column 5 and make an alloy. So you should take one gallium and one arsenide and form a gallium arsenide, gallium arsenide, gallium arsenide lattice. So that's one way to form it. Or indium and phosphorus, indium phosphide, right? Or gallium and nitrogen, gallium nitride. And for example, gallium nitride, one of the advantages of gallium nitride is that it has a very large band gap. So at very high temperatures, it's pretty stable. So if you want to make power devices that operate at high temperatures, gallium nitride may be a good thing to look at. But the key point to all of this thing is really the question of how we control this. Because this ability to dope with third column and fifth column, the donors and acceptors, will allow us to design devices. And we'll go through the process of the device design in the next several lectures. And in some of your homework problems, you also design devices. You will make devices that would do certain things. You target a certain kind of behavior and achieve that by doing this. So any questions on this before we move on to the next related area? Okay, so so far we talked about this energy levels and all those things, but the question is, what distribution do these kind of electrons, let's say electrons, will follow in a real system, particularly in thermal equilibrium? By the way, I want to clarify something, and this theme will occur again. Thermal equilibrium and steady state are not the same thing. They're two different things. And we'll see scenarios where this device is in steady state but not in thermal equilibrium. For example, when a diode or a transistor is carrying current, it's in steady state but not in thermal equilibrium. So right now what we're talking about is thermal equilibrium. So electrons are fermions. What's the definition of fermions? Anything with a spin of fractionals of 1/2, 3/2, etc., etc., etc. Now, and fermions follow the Fermi-Dirac distribution. So what is the Fermi-Dirac distribution? So Fermi-Dirac distribution basically gives you the probability of finding an electron with energy E. It is defined as 1 over 1 plus E to the power of E minus EF over KT, where K is the Boltzmann factor. (1.38 10 to the negative 23 joules per Kelvin), and T is the temperature in Kelvin, an absolute temperature. So if you actually plot this F of E versus E at temperatures above 0 Kelvin, it has a behavior that looks like this. And this is EF. At EF, the Fermi energy is defined essentially the energy at which you have a probability of having the probability of 1/2 of finding an electron, or fermion in general. Now at lower temperatures, let's say at 0 Kelvin, if you plot this quantity, you will see that it basically becomes abrupt. At 0 Kelvin, it is exactly like this. Now, what Fermi-Dirac distribution tells you is the probability of finding an electron at a given temperature, at a given energy, for a given temperature, in thermal equilibrium. Again, I'd like to emphasize this, thermal equilibrium. So now what does this mean? It basically shows you that there's a tail, exponential tail for something. So there will be always electrons with very high energy, but the higher the energy you're targeting, the fewer of those there will be. And there will be always the probability of not finding an electron at low energies, which basically, for example, can correspond to holes in conduction band, in the valence band, down here. Okay? So this is the Fermi-Dirac distribution. Now, one of the interesting things about this is that if you actually look at the Fermi-Dirac distribution and look at it, say, well, let's look at a special case. Let's look at the case where E minus EF is greater than 3 kT. So if E minus EF is greater than 3 kT, what will happen here? This exponential, this is e to the power of greater than 3. So this would be significantly larger than 1. So the probability distribution, the probability of finding something at the energy something, becomes proportional to e to the negative E minus EF over KT, which again by definition is proportional also to the E over KT. What does this look like? Probability of finding something with an energy of E of capital E being proportional to e to the negative capital E divided by KT. Boltzmann distribution. So this is Boltzmann distribution. So you can see that if you are more than 3 kT above EF, the Fermi energy, you can really use the Boltzmann distribution as an approximation for this thing. And you will see that actually for most of the calculations that we want to do for devices, the devices that we deal with, you can use the Boltzmann because we are in that situation. Similarly, for the probability of a lack of electron, so the probability of not finding an electron, the same deal. So here, if you are more than 3 kT below here, you can actually use a Boltzmann, or 1 minus E something, right? Because then that becomes so small if this is much, the opposite rate, if this is 1 over that is greater than 3, then basically it becomes e to the negative 3, so it becomes much smaller than 1, so I can approximate this whole thing as 1 minus this. And the interesting thing is that actually for a lot of device physics results, a lot of people go through the whole thing, write everything with Fermi Dirac distribution, and do a very complex derivation, or rather more complex derivation, not very complex. But then at the end, they make a simplification which is tantamount to using Boltzmann. So if you're going to be doing that at the end, you might do it at the beginning and get the results much more rapidly, much more directly. Now, there are situations where Fermi Dirac distribution does matter. So it's important to know how to deal with that. But in general, a lot of times, actually, that's not the case, many of the practical situations. So the other thing that comes out of this that's quite important is what is the probability? So if you have a Boltzmann kind of distribution, the question is, what is the probability of finding an electron with an energy greater than a known energy, a predefined energy E1? So if I say E1, I want to know what is the probability of, what's the number of electrons, or what's the probability of finding an electron with an energy above E1? Because this is the probability of finding it at E1. So basically, I have to integrate this from E1. So it would be integral from E1 to plus infinity of e to the negative of this thing, right? You can write it as E minus EF divided by KT, dE. So now this part of it is constant. So you get e to the EF KT if you wanted to. Keep that. And this part of it is just the integral from E1 to plus infinity of e to the negative E over KT, dE. And this integral is obviously going to be proportional to e to the negative E1 over KT, with the KT up front. Since it's proportionality, we just keep that. So we write it as e to the EF minus E1 over KT. Oops, not that e, lowercase e. Which is also proportional by definition to, okay, so now this is getting too cramped here. Okay, so it becomes, so that probability, so that's basically the probability of finding with a particle with an energy greater than E1 is going to be proportional to the e to the negative, e to the EF minus E over KT, which is also proportional to E1, e to the E1 over KT. So this is a useful result. It says the probability of finding an electron with an energy above E1 is proportional to the e to the negative E1 over KT. Now, this is particularly useful in finding the current voltage characteristic of a diode or a transistor and things of that sort. So this is a very useful result, and you will use it later, soon, to determine that. So now, if that's the case, now if you have an energy band diagram, so let's keep this here, and think about a semiconductor now. So now we want to become a little bit more quantitative. You want to say you have an energy band diagram, you have a valence band, and you have a conduction band. These are the edges of that. And then you have a Fermi Dirac distribution describing the probability of finding these things at a certain energy level with some Fermi level, EF. What are those probabilities? So the question is that because this probability of finding an electron in the conduction band tells me what the number of electrons, the density of electrons is, n, right? But according to that equation, this is going to be proportional to e to the EF minus E1. In this case, it's going to be EC over KT. So it's going to be proportional, the number of electrons, free electrons, is going to be proportional to the EF, the Fermi energy, minus EC, the energy of the edge of the conduction band, divided by KT. And I can call this proportionality constant NC. Now this NC has a name. It's called the density of states at the edge of the band. But anyway, so that's a proportionality constant. And similarly, for the P, for the number of holes, I'll have an NV associated with that. So it would be E of, it would be EV minus EF over KT. So there are two relationships that you can obtain. Now, this is generally true for any kind of semiconductor with any kind of doping. But so let's talk about the intrinsic semiconductor. So if you have an intrinsic semiconductor, meaning something that's pure, no doping semiconductor, what do these correspond to? Well, in the intrinsic semiconductor, we know that the N and P are equal, right? So N is going to be equal to P because the generation rate and recombination rate are the same. And also for every electron that you generate a hole. So the hole and electrons are generated but together as pairs. So their numbers have to remain the same. And we call this parameter Ni, N intrinsic. It's 1.45, 10 to the negative 10 to the 10 electrons per cubic centimeters, I think. It's 1.45 for silicon, or 10 to the 10 per cubic centimeter, if I'm not mistaken. Now, so that's Ni. So in that case, the Fermi level associated with that, we call the Fermi level associated with that EI. So EI is the Fermi level for the intrinsic semiconductor. So if I plug this into here, for intrinsic semiconductor, I get Ni equals Nc e to the EF minus EI minus EC divided by KT. And for similarly, since that P is also the same thing, it's going to be NV e to the EV minus EF over KT. Well, not minus EI, because it's now intrinsic. Right? So now I can use this relationship to simplify what I wrote up there. Right? So, and write it in terms of Ni. So now we can say, hey, I know a part of this is here, the NCE to the EC, negative EC over KT of it is there. So I can simply write that as Ni e to the EF minus EI over KT. And similarly, this would be Ni e to the EI minus EF over KT. So this is a useful thing. What it says is that the intrinsic energy, the Fermi energy, which is somewhere in the middle, with respect to the Fermi energy wherever it is, your actual Fermi energy, with respect to EI, this difference, this distance in energy, this delta in energy, determines the number of electrons or holes you will have. So if my EF is above EI from this equation, do I get more N's or do I get more P's? Let's say I have a situation where EF is above EI, like the one that's shown in this picture. Do I have more electrons or do I have more holes? More electrons, right? Because it's EF minus EI, so this is a positive thing. So it's a positive exponent, and this is a negative exponent. So it would be an N-type material. Now, if my EF was below EI, this would be a P-type material. So now, but from these two, you can also get something much more, familiar probably, and quite useful, is that if you multiply these two, what do you get? You get N times P equals, these two cancel, Ni squared. So the product of the number of electrons and the holes is constant. Right? So if you get more holes, you get fewer electrons, and vice versa. And this is an important element of this. So the last thing we are going to talk about briefly is a quick discussion of this picture and how it affects the way you design semiconductors. So think about it this way. So think about a piece of semiconductor, right? And let's say what happens if you actually introduce, and we'll discuss this in more details, if you introduce different kinds of dopings in different locations. So let's say first they're detached. So let's say you have two pieces, and you have some donors introduced here and some acceptors introduced here. Right? So when you have introduced the donors, what have you done? You have created more electrons, right? Because they have more free electrons. So here you have an N that's greater than P. So it's an N type. That's what we call it. And here you have a P that's greater than N. So you have a P type. Now, if they are sitting there and nothing is happening, they're going to be in thermal equilibrium individually. Now, when you bring them together and attach them to each other, so let's say now you've attached them to each other, and you let it settle, which will happen very, very, very quickly in semiconductor. The thermal equilibrium happens very quickly, and we'll discuss why later. Still, it's in thermal equilibrium. So the Fermi Dirac distribution still holds. So you have the same Fermi energy across the whole thing. What happens, though, is that the energy band diagrams have to be bent with respect to that Fermi energy. And again, we'll see this in more details later on, as you basically go from a situation where your Fermi energy is closer to the N type to a P type. But if you are in thermal equilibrium, which basically means that there's no heat exchange, I mean, the thermal equilibrium, there is heat exchange, but there is no net flow of heat going in or out, you will have an energy band diagram like this that we'll discuss in more detail later. Now, but if you, for example, have a current flowing through this, even if it's a DC current flowing through it, it is going to be in steady state. You can have constant current flowing. But because of that constant injection of energy into the system, you're not in thermal equilibrium. The same way that if you have a hot reservoir and a cold reservoir, and if you put some sort of a thermally conductive material in between, there will be a constant flow of energy from one side to the other. So there will be steady state flow of heat. But that system is not in thermal equilibrium. So I want to emphasize the difference between thermal equilibrium and steady state. And we'll see this more frequently next time. So next time what we will do, we'll take this and then use the energy distribution and then the energy distribution as well as the velocity of movement of electrons inside the semiconductor when we calculate that to find the conductivity and resistivity, which we started with today. Now we are going to calculate the conductivity in terms of these microscopic parameters. And we'll see what makes a semiconductor really a semiconductor. Right? Any questions? Right? Well, see you on Thursday. Thank you.